Okay, so now I'm ready to introduce the first speaker for our summer school. This is Professor Ikeda, and he'll be telling us about Schubert polynomials. Equivariant Schubert polynomials. Please help me welcome Professor Ikeda for coming.
Thank you very much for the introduction. First of all, I would like to thank all those who to help organize the conference and all those who have come here in Osaka. I'd like to talk about equivariant Schubert polynomials. My topic is polynomial. Polynomials that represent some class, represent classes, Schubert classes in some homomorphism. First example is torus equivariant homomorphism, and in the Friday, so lecture I will talk about K-theory Schubert class. And the basic problem is to find good representative for that Schubert classes. And many attempts have been done on this problem to find good representative of Schubert classes. But in this lecture, I want to convince you that the polynomials that represent the Schubert class is in some sense unique. So my ambition is to reverse the arrow to find unique polynomial that represents Schubert classes. So the polynomial that class itself, polynomials of class itself. So in doing this, one idea is to consider the infinite rank case. I basically think about the classical type of B groups. And if you consider the infinite rank case, the polynomials can be singled out in some condition of state stability with respect to the ranks of the groups. And one more idea in my lecture is to use the restriction maps to the torus fixed points. In the infinite rank case, infinitely many points correspond to the torus fixed points. We have infinitely many restriction maps to each torus fixed points, and this single out the unique representative of that class. So I will show you how to realize this idea in concrete, using very concrete polynomials. Okay, so I will start with today I will talk about ordinary glass manifold of P-planes in CM. And I will give you some basic ideas in today's lectures, and tomorrow I will extend this story to other classical types. And in the Friday lecture, I will extend this to case theory case. So this is so today lecture is a basic case. Anyway, a point of Grassmannian can be represented by choosing a basis of the space, linearly independent. So we can make a matrix like this. If these three something like this. By column operation, we can we can choose a base of this form. Here the pivot ones are located in 1, 3, 6 times 6. And we can consider this as a subset of Grassmannian, an open subset of the Grassmannian, isomorphic to affine space of D times D minus D. I will denote this open set by U of some label, lambda. I will explain, I will specify the label later, given by Young diagrams. And we also consider affine subspace consisting, defined by the conditions of these coordinates. Or above the pivot ones are 0. This is called the Schubert cell. Then we have a decomposition of our Grassmannian into the set of into a family of Schubert cells. And the important ingredients of my lecture is action of torus. I will denote T by the torus of diagonal matrices in GL and C, and we consider the action from the right to our Grassmannian. So we want to consider the weight of these coordinate functions concretely. The weight of coordinate functions. I will denote it Zij dual to some star like this is given by Ej minus Ei. What is the indices means? In the ith row, if we have star, we have 1 like this. Ith row, we have star and so representing arbitrary complex numbers, and we have pivot 1 in the 0th round. Then if we multiply by the left, the diagonal matrices. Diagonal C1. This becomes CI, CJ. So this corresponds to the same point in our Grassmannian with CI divided by CJ. So it tells us that the function, coded function of this star is has weight like this, because we are the function is dual to this point, so we place dj minus dy in between in additive way. I will use these conventions throughout the lectures. And also, I have to explain the labels of this. Actually, this is nothing but the shape of this squared star rotated to the left by 90 degrees. We consider it as a Young diagram. We also, it is convenient to consider the label as the following one. We place 1, 3, 6. Place the position of the pivot points in this way. This shape can be made from this by something. 1, 2, 3, 4, 5. Our Young diagram is inside the rectangle of D by n minus D, and from here to here we make arrow. If the box is occupied, we go up. If the box is not occupied, we go right, making this path. So we have a Young diagram inside this rectangle. This is the label we use. So this correspondence gives bijection between this offset space which is naturally, each element can be naturally represented by the diagram like this, because this is a orbit of this diagram. The occupied boxes. And then we identify this set with the set of partitions inside this rectangle. So more precisely, these data lambda. So this is the label we use. Then so the co-dimension of this cell turns out the number of boxes in our type. And I also need to record the weights of these coordinates like this. 1, 2, 3, 4, 5, 6, and we record the weights of the corresponding coordinate functions. This 6 minus 2, 6 minus 4, 6 minus 5, 6 minus 2. I will call this the weighted Young diagram in this way. It is just the record of the weight of these functions defining the sugar cells inside our chemical neuron. We have a natural order of these labels by the defined suppose this is actually the inclusion relation between the Young diagrams. This is defined just so bigger mu is bigger, lambda is inside diagrams. Then we can define Schubert variety this way. The disjoint union of Schubert cells less than or equal to lambda. So of course the coordination is given by this number. And it is easy to see that the condition that a point of the Grassmannia belongs to this set is equivalent to the following linear algebraic conditions using graph. This is the ordinary definition of Schubert variety. This is here I use a conventional standard graph from like this. This is equivalent. So this is Schubert variety. Now, let me just write down first theorem of our story. First theorem is equivariant homology of the Grassmannia is actually a direct sum of equivariant Schubert class parameterized by a set of diagrams. Of course, I have to explain the definition of this guys and this guys. So, but I want to show you what is this. This is first. In order to define these options, I will use a combinatorial approach using GKM or moment graph. This is a kind of weighted oriented graph, if I suppose. The vertex is intersection of the radius of our indices. Actually, in geometry, these are the fixed points, the set of fixed points inside the Grassmannian. And because they are weighted arrow, connecting these points, if lambda mu level alpha, if mu is given by a reflection corresponding to alpha. Actually, alpha R is a positive root. And speed of number. It is convenient to explain this relation by using this picture. So, for example, if lambda corresponds to this diagram, and mu. This diagram can be obtained from this by moving this to this box. So, if the position of this block is I and A, the deflection operator is actually the transposition I inside SA. And alpha is alpha Tj minus Ti. If we denote the corresponding torus fixed point by E lambda, this condition is actually corresponds to the T stable P1 curve inside our Grassmannian with lambda E lambda and mu. And the weight, I think it's the weight alpha should be minus alpha. This is a geometric thing. I just make calculation by using these combinatorial conditions, but actually the geometric mean is given by this one. using this structure, I can define. It's clear. I will show you a small example. I will show you. If you look at the point of lambda like this, we have 3 arrows into this point, lambda, with label like this. So this diagram can be obtained from moving this box to this. So the weight is 4 minus 3, like this. There are actually, if the diagram has, now we have 3 boxes, so 3 arrows into this, into the point. So the weighted and the diagram corresponding to lambda is in actually bijection with the mu, the set of points or vertices into E mu to E lambda with label alpha. Actually, each box corresponds to each arrow into this point. And this projection is weight preserved. This weight naturally corresponds to this weight. Then we can define our name of equivariant emoji as the so-called GKM conditions. This is actually as a subnet or subnet product. So we associate to each x points a polynomial in n variable in t variables t. And the element is inside. If you write the element of the map like this, this is a definition. This is inside this. If and only. And I mu is divisible by the label alpha. Is connected to U by the alpha for each. There is a delicate problem of the coefficient of the cosmology, but I don't want to touch the point. I just want to define the ring combinatorial in this condition, by these conditions.
Don't you need divisibility if the arrows pointing the other direction as well? You define your arrows as unidirectional. It's just the edge.
Sorry?
So at least your picture over there, your arrows are definitely going in the other direction. There are 3 in and 1 out of your diagram, but in fact, you should have, there's 4 in.
4.
Oh, I'm sorry, that's, never mind.
So consequence of this condition is that if we have an element of a ring, a basic lemma is as follows. If we have an element of the ring, and if mu is minimum in its support mu defined by this then this polynomial is divisible by the product of the weight of some inversion set mu where the inversion set of mu is actually these incoming arrows. So alpha, I will denote the set of positive root. These are, I'm sorry, I didn't define. This is the set of linear form like this. Positive root. Such that note that we have action Sn, the y root over Gn. Then we have natural action of the set of partitions by using this identification. So I just write alpha, the reflection of our foundation groups. So this is because if you have element of our equivariant homology, and minimal means that this is minimal with respect to this ordering. So if you have this is a minimal point, then we have zero value for each vertices into these points. So by the conditions, this element should be a multiple of these linear forms. But in this case, these are relatively prime. Thereby, it's relatively prime, and we are, the ring we consider is UFT. So the element, the value of the minimum point should be divided by the product of weights. This is technically the main point. I should have said the reference of today's lecture is I am basically follow the paper by Professor Alan Knudsen and Helen Stow. You know, there is a famous paper of puzzles, equivariant puzzles and equivariant homology of class matrices. by Alex. I basically follow the argument of this paper, but I just emphasize the property of polynomials. But these arguments are all explained in this. So I cannot repeat it, but this is important. So then I have to explain this Schubert class associated to a double lambda. I also take a combinatorial approach to define definition Schubert class. Sigma lambda over mean is called is a Schubert class associated corresponding to lambda if the following conditions are satisfied. First one is not so important. The degree, if we count the degree of polynomial for each variable ti by just 1, actually the topological gradation is the in, and we should multiply by 2, but I just count by degree ti by 1. Then this is homogeneous of degree. And this is the most important property. I will write the value of this value of this element at this point by this symbol, because it is it has a meaning of restriction to Cauchy-Torres fixed points. Unless we have a relation, order relation like this. This relation has a geometric meaning that if you denote the torus fixed points corresponding to mu by E mu, then this condition is the point is on the variety. So it is a natural interpretation, natural meaning. The third one is a certain normalization, lambda divided by d lambda. This is I should define this. I should define this. I should this product is actually this product. This is the definition. I will give a combinatorial proof of the existence of this class by using special polynomial. And also, if you admit that this ring has a geometric meaning, the existence is obvious from geometric meaning. But now I stick to the combinatorial approach. So if you want to prove the existence, I have some words, but the existence can be proved by using factorial Schur functions I will discuss later. So existence comes from geometry and second from combinatorics. And there is at most one Schubert class to each level lambda. Actually, the Schubert class is unique. This is a direct consequence of this lemma. This is a simple consequence of this lemma by using degree consideration and this ordering. So, and also we want to show that these elements are linearly independent over this ring, and they span the ring. This is also a consequence of this lemma. We can, if you have an element of this ring, we can subtract some linear combinations of these classes one by one to reduce the support, and finally we get we finally represent the element as a linear combination of these classes, Schubert classes. This is also a direct consequence of this. We can see the detail. It is not so difficult, but the detail can be found in this paper. Now I want to talk about the functions called factorial Schur functions, but I just want to make a remark. We can consider infinite lambda case. We can define for each partition lambda inside P, simply P is partition of at most D parts. For each D part, we can define consistently some element inside D, defined in a similar way to the polynomial ring of infinity. Just like this. You can define in a similar way. You can define in similar ways using CKM condition inside this product. And we can consistently introduce an element inside this thing. This is actually a natural extension to infinite lambda case. This is one comment. And in the remaining part, I want to show you special functions that need to be represented. The class by only one polynomial. So this is defined as now we have, suppose we have a partition of at most p power like this. Then the factorial Schur function is defined as follows. This is actually a symmetric polynomial in d variables and the parameter, some number of parameters t. This can be defined as a ratio determinant. I to J. This is divided by difference product. Here, the symbol is called generalized factorial. Defined this way. There are some history for introducing this polynomial. But I don't want to say it completely. Anyway, this is called factorial Schur function. This is actually an element of the symmetric polynomial in d variable. This parameter in t. Actually, we need only lambda 1 plus b minus 1, 1, 2. But anyway, I will use this. I prefer to use this infinite case. This is called factorial Schur functions. Actually, my claim is that this is exactly the Schubert class in this sense. So we need a simple algebraic idea of substitution. Localization or restriction. Or substitution. This is a simple idea. If you have a symmetric polynomial in d variable, symmetric, and suppose we have a element of our label. This actually is considered to be a plus fixed points. Actually, we consider it as a plus fixed points or plus minus. And we can pick a, because this set can be naturally in bijection with the coset space. So we can pick a permutation V to representing this permutation. Then we can make the following substitution. And I will denote it by simply by T mu. It doesn't depend on the representative because we have symmetric functions. Then this simple idea is then we have, if you consider this map product, the map of the product inside by making all answer. This is ring homomorphism of sorry. Extend. Sorry, I'm very sorry. I just want to say that this is actually an element of our GKMP because this kind of substitution makes these families of polynomials satisfy the condition of divisibility of GK. So the theorem is this is a limit. So the theorem is that making this substitution, this kind of substitution, this is the first series of variables. Then we have a equivariant class restricted to the torus space mu. This with some tau, I think, and slightly different complex, pepper and iman. This is the main theory, main result of today's lecture. And the corollary, we can consider infinite rank situation. Then, actually, the map file in the infinite rank case gives isomorphism of ring GD equals infinity, sending the factorial functions to the equivariant Schubert of infinite version. So in this sense, the factorial Schubert function is naturally identified with equivariant Schubert. This is the unique one. Make this to make. So I just want to make some comments about the proof of this theorem. As I discussed before, the equivariant Schubert class is characterized or defined by the vanishing and the normalization. And because we have a very concrete expression of this polynomial, we can directly check the conditions of vanishing and the normalization enjoyed by the image of our mind. We can directly show that the image of our factorial Schubert functions satisfy the defining conditions. One thing, we just it can be done by using the definition of the ratio of determinants. And one hint is, I think we can pick up any representative, but I think it is useful to make this complete representative. By this substitution, we can directly check that the function satisfies the vanishing and the normalization. Actually, the numerator of this is the determinant over the difference product. So we can, if you substitute the variable like this over the matrix, then the matrix becomes very simple form, and then we can directly show that the vanishing. And also, because this is an image from this map, it satisfies the decay conditions. So we can identify the image with the equivariant Schubert class. So this is the main result I want to talk today. So yeah, so if you have some time for data use, I just comment on a few words about the divided difference operators. Basically, I think in some sense this is the end of the story, but we can prove this result by using another technique, using divided difference operators. I want to use it in the Friday lecture, so divide the difference. Let divide difference. This is now we consider the ring homomorphism between the ring this and this is isomorphic to the GKN subring in infinite rank. This is actually the direct sum of this is free over ZT, and the base is given by this equivariant Schubert class. And this is isomorphism as ZT algebra. Then we have operations of both sides of the ring. I denote delta I. For symmetric functions on the left-hand side, DIF is defined in this way. Ti plus 1 minus Ti. In my convention, this is positive ones. This is not popular, but I use this is positive ones. This R acting on the polynomial in TT by exchanging ti plus 1 and ti. This is for left-hand side, and we have another one for on the divided GK thing. The formula looks the same, but the action of while group is different. The point is the action on the while group on the left-hand side, right-hand side. So while group Sn acts on our GK sub by the following form. If you have an element of this thing, and if W is an element of our while group, then this is defined. Because the while group acting on our set of labels, partitions, so we can find this is the action on the set of Young diagrams, natural one, and this action is on the natural action. This action is natural one on this computation by T i's. So one result is that the equivariant Schubert class satisfies the following conditions. If Ri lambda and 0 otherwise. So we can find a proof in the reference paper, and we can also try by itself. And I think it is a good exercise to work. So my claim is that this action commute with this map. So we can directly show that the polynomial satisfies the same condition. This is of course true because we have the theorem, but it is a good exercise to figure out what is the Schubert functions. This is also directly checked by using the formula, the complete formula as this. Okay. So tomorrow I want to extend this story to the case of symplectic case. Basically, my favorite one is Lagrangian Grassmann. This is a certain homogeneous space of symplectic group. And the corresponding special function like this is called factorial Q functions. So this is the topics of next lecture. And in Thursday, I want to give an exam application of this result to the singularity of Schubert varieties. And in the last lecture, I want to generalize this story to equivariant K theory case.